This is StarTalk. Neil deGrasse Tyson here, your personal astrophysicist. I got Chuck Nice with me. Chuck.
Hey, Neil.
Yeah, we got a Cosmic Queries.
Yes.
One that's backed by popular demand.
Oh, one of the most popular.
Oh, yes. We had my friend and colleague Brian Greene, theoretical physicist, professor of physics and math at Columbia University, author of the very best-selling The Elegant Universe, followed by The Fabric of the Cosmos, followed by The Hidden Reality. My boy's into all kinds of freaky cosmic stuff, and we got him back for more by popular demand. Brian Greene, welcome back to StarTalk.
Thank you. Good to see you guys.
Yeah.
Yeah, for those who are watching this on video, I think that's a black hole behind your head.
It is.
Full wall-size
They all
black hole.
look just like that.
That's awesome.
Did you just emerge from that black hole for this interview and then you return through it?
If I had done that, I would have broken the laws of physics. You know that. So.
We can't have that. No.
Yes. But all of your knowledge would still be intact. Or is that's information? That's information.
A very good point.
Yeah.
Subtle point. I don't know how many of your audience just got the subtlety of Chuck's comment, which is quite
My boy Chuck,
deep.
I gave him a little diploma recently.
Yeah, I know.
For how much he's learned of physics. I created just a little sort of StarTalkian diploma.
Well,
because
declared.
Yeah, I love it. Let me tell you something. It's the reason I do this job. It damn sure ain't for the money.
So speaking of money, I just wondering. So Brian, why you have two professorships? Was one not enough? Professor of physics and professor of math?
Yeah, each department doesn't know about the other, which is
My boy's drawing two paychecks.
Oh, that's so funny.
Okay, StarTalk fans, don't tell anybody.
Exactly. We meet every day at a very small cafe. Me and the math department.
It reminds me of our colleague, Sean Carroll, who moved from Caltech to the Johns Hopkins University. He has a dual appointment there in physics and in philosophy.
yeah.
Yes.
Yeah, so they're feeding his interest by those two affiliations. So I guess that's what's happening with you, right?
To some extent, yes. You know, I started out as a math kid and then became a physics nerd. So, you know, it goes way back for me. In fact, you know what? When I was in junior high school, went to the math department of Columbia, and that's where I first really learned advanced math. I just knocked on people's doors and say, teach me stuff. And one graduate student took me on.
Wow. Wow, you and Neil have something in common. See, kids, you better learn something, okay? These people at universities, I don't care if it's Carl Sagan or the math department at Columbia, they have time on their hands.
No, I'm just saying if they see someone young and ambitious, you can't turn
that away. No,
you can't turn that away.
You can't turn that away.
Totally.
Not given the culture we've cultivated here as a nation that values achievement and excellence, or at least most people do, I think. Okay, some people do.
Yeah, I was gonna say we are two nations.
All but 37% do.
Exactly.
So Brian, I remembered, did you tell this to me on the air or was it offline, that you were not interested in a book unless there were equations on the pages?
Yeah, we did, I think, talk about that once. When I was in college, I would go to the bookstore to look at the assigned text for a science class. And if there were a lot of words, my heart would sink. If it was chock full of equations, I was like, okay. Because, you know, words can be ambiguous, but the equations are so precise that certainly at that time was what I was drawn to more fully.
Okay, so Brian, what you're saying is so that none of us misunderstand you, you should only speak in equations for the rest of the conversation.
Perhaps I should add, I've matured since those early college days.
Oh, okay, you're taking on some vocabulary.
Human being has become more important to me.
I'm just trying to figure out what book is sitting in Brian's bathroom right now. That's all.
I remembered my freshman year, because I go way back. I predate you, Brian. I was taking a computer class back before computers had their own department.
Yeah.
Because it was not yet enough of a thing to justify an entire academic commitment by a university. But anyhow, I was becoming very fluent in Fortran. And then I had my first dream in Fortran.
Yeah.
And I said, "Oh, okay. I guess I've crossed over."
Wow.
I have not had one of those, but I have had my first lucid dreams. Have you had any of those?
Oh, these are the kind of people where they meet aliens and things, right?
Well,
That's where.
Well, at least mine wasn't. Mine was a dream. Yeah, I think the conventional definition is when in the dream you become fully aware that you're dreaming. And
Yeah.
Oh,
You realize
that's
that.
different. I was
Yeah.
thinking, okay, that's different.
Yeah.
So, okay.
Which is
No,
a very
I never
cool
had one of those.
experience. If you, yeah, it's a very cool experience. The first time I said, I know I'm dreaming because the architecture of the building was different from what I knew it to be. I said, this must be a dream. I'm going to prove it. I'm going to prove it by waking myself up. And I shook myself in the dream and I woke up in real life.
Wow. So the architecture of the building is what gave it away. That's interesting.
Absolutely. Yeah.
So you want to know, here's the thing. I had a lucid dream where I was on stage and I was doing material I've never done before. I was literally writing material in my dream. And here's when it dawned on me that it was a dream. I was bombing. And I was like, I cannot believe I am bombing. And then it occurred to me, wait a minute, this isn't real. And I'm in the dream. And I was like, I'm waking up. And then I woke up going, Jesus Christ, you have a dream and you make yourself bomb in your own dream. Like you could have had a dream where you were at Madison Square Garden, but instead you're at the same comedy club you always work at and you're failing.
Well, it's usually anxiety-driven dreams, man.
That's what that is. That's an anxiety-driven dream. Yeah.
Well, Chuck, we got questions lined up for Brian.
Yes.
From our Patreon members. $5 a month gives you access to the genius of Brian Greene.
Well, listen, and that's a deal you're not getting anywhere, man.
You ain't getting anything like that.
$5 a month. I have to calibrate the answers to reach that level. Parts to your audience.
No. The idea is it's a bargain, Brian. You're not supposed to give them the actual value. It's a value-added service.
Yeah, it's the entry level that people have access. There you go.
There you go.
What do you have?
Let's go to Colin Brum, and Colin says, does quantum mechanics prevent an infinitely small singularity inside of a black hole? I thought nothing could be smaller, check it out, than a Planck length.
Yeah.
Oh.
So if we're infinitely small, how do we violate that precept?
Yeah, Brian. You got one with a black hole above his head? What? Wait, let me preface that by saying, didn't Einstein, or was it Hawking? I think Einstein say, there's got to be something to prevent the singularity because that's just not physically, God is dividing by zero there. So there's got to be something to prevent it. We just haven't discovered it yet. So where does all that
You're
land?
absolutely right. In 1939, Einstein wrote a paper where he basically tried to prove that the mathematics that suggested a singularity at the center of a black hole could never be realized in the real world, in a real world situation.
And just to be clear, singularity is infinitely small, infinitely dense.
Well, I'd like to rephrase it because, yes, that's the language that people often use. But to me, singularity really means any place where our mathematics can't give us insight to what's going on, any place where the mathematics breaks down. And so that's an important point because to the questioner's question, when we get to the Planck length,
Wait, Brian, it's a cop-out, but I like it. It feels like a cop-out, but we'll ride it.
The
Go.
reason why it's not a cop-out is because if you take the mathematics too seriously and you push it into infinitely small or infinitely dense, then you do run into the kind of questions that the questioner asks. Like, doesn't that conflict with the statement that you can't really go smaller than the Planck length? And those are just two different perspectives. One is going to take the math and just push it regardless of how far it's going to take you. The other says, let's really evaluate step by step whether this math is actually applicable. And so this is the more sensible perspective.
Okay, so you're saying it's a mathematical singularity, not a physical singularity.
That's the best that we can say today. Now we need to go further.
Okay.
It's not enough. So now pop out.
It sounds to me like it's the terms that we use. We don't have the adequate language to actually describe. Because when you say infinite, one thing comes to mind, okay? But the fact is that it's really not infinitely
I suspect
small.
not. But here's again the point. Since we can't actually do the experiment, we have to rely on equations.
Right.
The equations just take us so far because the equations are beautiful. They not only give you insight, they also tell you we can't give you insight into that domain. We're not powerful enough. We're not refined enough. And the equations clearly tell us that going smaller than the Planck size or higher than the Planck density is beyond the reach of today's equations.
Remind everybody about a Planck length.
So a Planck length is a very specific number. It's about 10 to the minus 33 centimeters. It's incredibly small. And you might say, where in the world does that length come from? Well, it comes from combining Newton's gravitational constant, Planck's constant from quantum mechanics, and the speed of light. If you put those together in the right way, a length pops out, and that length is the Planck length, 10 to the minus 33 centimeters. And its importance is the equations pretty clearly say, don't push us smaller than the Planck length because we're not applicable in that domain. And people who talk about infinitely small are disregarding that and saying, well, let's just keep on going and see where the math takes us. And it takes you to a crazy place. Infinitely small, infinitely dense, singularity. We need to fill in smaller than the Planck length or whatever new idea for length comes into play in order to have a complete theory of the world. We don't have that yet. So we sensibly should stop at the Planck length because that's where the math ends its applicability.
Okay, so what you're saying is that since the mathematics we create that represent a physical idea, what you're saying is that mathematics, which is, let's say, general relativity, admits that there's a point beyond which general relativity does not apply.
Yeah, especially when you put general relativity and quantum mechanics into a combined theory. So general relativity alone doesn't have the Planck length in it because, as I mentioned, you need Planck's constant from quantum mechanics. Mechanics doesn't have the Planck length on its own either because you need Newton's constant from Newtonian gravity or from the general theory of relativity that both make use of that number. So it's only when you try to have a more complete description that you have all of these ingredients. And when they come together, we are told from the math, hey, you've got to start thinking differently when you get to the Planck length.
But it sounds like worlds collide. Worlds colliding, Jerry. Worlds colliding. That's what it sounds like.
It kind of is. Right. I'd like your what did you call it, Brian? A shotgun wedding between quantum physics and general relativity in the early universe, where the two were had to get to know each other for the first time.
Hot and dense and small that you needed both a theory of gravity and a theory of quantum physics.
So, Brian, my sort of terrestrial version of that, I think of lines of longitude on Earth as separating time zones, 24 or so time zones that we have. But of course, as you move away from the equator towards the poles, these lines of longitudes get thinner and thinner, right? There's like the slices, like when you slice an orange from the top down, they get narrower and narrower, and they meet at the pole. So you can ask the question, what time is it at the North Pole? And there is no time. It has no meaning. That question has no meaning at the North Pole, where all time zones meet. And so that's my baby example.
And actually, that pulls out a very important point, because that analogy played out historically with black holes and black hole singularity, because you know, of course, that on planet Earth, there's really no singularity. There are other ways that you could define time zones that wouldn't run into this particular problem. So it's really a singularity born of human invention because of the way we set up these lines. People early on with black holes thought that certain singularities were real, but they turned out to be the analog of that. Coordinate singularities, bad choices of lines of longitude, if you will. And that's what happens at the edge of a black hole. The edge of a black hole people thought might be singular, but it turns out that it is not. But way down at the center, that's a real one, mathematically speaking, if you push all the way down, as we said, to infinitely small size. You can't get rid of that one by a change of lines of longitude, change of coordinates.
So watch your coordinate system.
Yes.
Is what that is. Right.
Man,
All right. So let's keep going. Chuck.
Thanks, Colin. What a
We
great.
spent a lot of time on that.
That was a great question. I mean,
let's go faster. Go.
William Silverman. And William says, hi, Dr. Tyson, Dr. Greene, Lord Nice. From a photon's perspective, does any time pass as it travels at the speed of light? If no time passes from the photon's perspective as it makes its journey, but the light years pass from the perspective of the observer, was it, here's the term, predestined to hit my retina when it left its source? From Bill Silverman at Lafayette Hill. So he's getting philosophical.
I like that.
My man took the physical and got philosophical, which is it's a weird concept when you think about it, but it makes sense.
Yeah. You know, it's a good question, because when you look at Einstein's special relativity, you find that the faster something is going, the slower time elapses as you observe time passing on that moving object. You know, so as something goes closer and closer to the speed of light and we're watching it, time will elapse ever more slowly for it. So if you take that to its logical extreme, at the speed of light, no time would be elapsing for a photon. Now, poetically, that's true, but when we try to interpret it in human, we make a real error, because a photon doesn't have any consciousness. It doesn't have any means of reporting experience. Those ideas don't really have any relevance. So to say that time doesn't elapse, so a photon doesn't age, is a very human description of what's going on. And this is a perspective that we humans could never have, because massive bodies can't ever travel at the speed of light. So there's a barrier for us to ever really know what that experience would be like. But there's a second part of the question, which is predestination. And I don't think that has much to do with the notion of how time elapses at different speeds. It has to do with how the universe evolves. And yeah, I do think that the universe evolves by laws that do not have an opportunity for humans to intercede. And so is there a kind of predestination built into physical laws, even with the probabilities of quantum mechanics? Yeah, I would say, yes, there is.
But wait, but let me make a practical example of this. So if a photon leaves the center of the galaxy, okay, my thesis data was on stars at the center of the galaxy. Yeah. All right. And I would always think each night that this photon has been traveling for 35,000 years and it hits my detector instead of someone's buttocks on a beach. Okay. So I get, I'm giving value to these photons, all right, or a mountainside. But my question is, if I were able to watch it travel and stick a mirror halfway through to just send it off in another direction, then the photon on being emitted didn't know I was going to do that. And so it wasn't going to hit my detector.
Yeah.
So the photon that's emitted and absorbed in the same instant, because it has no concept of time, could that have been anything else? Could that have had a different fate than the one I gave it?
No, but I would also say that your act of putting the mirror was also predetermined in a similar sense, that you're a collection of particles governed by physical law. And I don't believe that you have intrinsic control over those particles, because you don't control Maxwell's equations. You don't control Einstein's equations. You don't control things.
So you think.
As far as I know.
As far as you know. Yes.
So yes, the events of the universe play themselves out in a manner that's dictated by physical law. And that means that human freedom of will that we ordinarily feel that we have, I think, is of a different variety than we intuitively think. When I lift up my hand, I feel like I've made the choice to lift it up. When I think about it more fully, I truly believe that it was the laws of physics that required that to happen. And I just am observing how my particles are moving.
All right.
All right. That's. I'm sure that was disappointing.
Right about now, this is when Chuck pulls out some weed. Okay,
I'm talking about pull out. It's sitting right here.
I
don't have to pull it out.
All right, what else you got, Chuck?
All right, here we go. Let's go to Liam Cochran, and Liam says, "Hey, this is Liam from Rhode Island. What is it that string theory proposes that the fundamental particles we know, quarks, gluons, etc., are comprised of a combination of strings vibrating at different frequencies rather than just another type of particle? What is the purpose of the string idea behind an analogy to help people understand the theory in more simple terms? So, why not a particle that makes up the smallest particles instead of this idea of a vibration or string that causes it to be more easily understood? Why?
Yeah. And Brian, let me prepend that by asking, are you proposing that everything's made of strings just so that it's more elegant?
No, certainly not.
The man who wrote the book, The Elegant Universe. Is this a philosophical motivating force for you? Because Kepler had his own philosophically motivating mathematics where the planets were platonic solids, and it was beautiful because it was math, and are you, what confidence do we have that you are describing reality and not a reality you want to be true, so that the universe becomes elegant so that you can sell more books?
We're hip to you in the industrial string complex. We know what you're up to, Brian.
So that is a key question, not the selling of the books one, but what is the role of aesthetics in making these decisions? And I would say that we theorists do use mathematical aesthetics at times, but in the end of the day, it's observation, it's experiment, and real tension in existing understanding that drives our ideas. So we began this conversation with a questioner asking about the Planck length and this tension between gravity and quantum mechanics. And I said, we need to go further, because just saying that they come to loggerheads at 10 to the minus 33 centimeters is not enough. It's not an answer. It's simply letting you know that you can't trust anything beyond that point. String theory is an attempt to fill in the gap, to try to put general relativity and quantum mechanics together. And at least on paper, and we've known this now for many decades, it succeeds in putting general relativity and quantum mechanics together.
Whereas if it's just a portfolio of particles, you don't get that benefit.
Well, here's the interesting thing. If you said that to me 7 or 8 years ago, maybe 10 years ago, I would have said, yes, you're absolutely right. There's a lot of progress that's happened. And now we realize that a lot of the qualities of string theory have a dual description, a sort of mirror image version in which point particles do play a role in that description. It's a description that differs from the way we describe point particles in the 70s and 80s in certain very specific and important ways. But we're beginning to learn that string theory is one language for describing this unification, but there are other languages, and languages sometimes do invoke point particles. So it's all kind of coming together in a beautiful tapestry, and we're still trying to, figure it all out.
Wow.
And Brian, it's been 40 years, so I'm very disappointed.
I
thought you all should.
Brian.
I thought you ought to have this solved back in the 90s.
But, do you mind if I actually address that? Because I know it's like partly a joke, but there are people who with a straight face really do say that. You guys said you'd wrap it up in 5 or 7 years. What's going on? And I just have to keep educating them that science is not like, a company where you lay out your product development timeline.
Right.
You have goals, and as you're going toward those goals, new ideas emerge. You follow those new ideas. They take you to wonderful, crazy places. And as long as you're not stuck, and we're far from stuck, that's what exploring the unknown is all about. You just don't know how.
Yeah, but what's weird is, like, when you put it that way, it kind of sounds like someone is saying to you, now the assignment was figuring out the entire universe. Why are you late? Why is your paper late? All I asked you to do was figure out the entire universe, and yet here you are saying you need more time.
Yeah. Okay, so I have said this publicly to Brian on stage. So this is not differently mean sounding than when I first said it. It's the same. It's okay. I've asked string theorists, what's taking you so long? And they say, it's a hard problem. And then I said, wait. So I said, maybe you are all just too stupid. That's not a consideration here, that we need a different crop of people to enter your field?
Well, I would say it somewhat differently. Yes, we always love young.
Of course.
We always want young students, who are vibrant and energetic. So I agree. But could it be that the human species is too stupid? Yeah, that's a real possibility. I mean,
there's a lot of evidence to back that up. I'm just saying, as track records go, let me just come down that I'm in the camp, the too stupid camp. I'm down to believe that.
No, but we can even take it out of our species, right? I mean, I respect the intelligence of dogs. They do some remarkable things, but they don't do quantum mechanics. So there's a species that has a limit on how well it can understand the deep laws of the universe. And so why would we be any different? I think it's a miracle.
We're not some limit of understanding here. Right, of course.
I think it's a miracle how far we've gotten.
Is that problem also exacerbated by observation, the inability to actually observe?
Yeah.
Because, honestly, that's what we do. We observe first. And then...
Right, so Chuck, here it goes. Ready? All right, so Brian, what particle accelerator do you need now?
That was funny.
It's just in a sense of scale. So take that Planck length that we mentioned before. Okay, if you take the Planck length is to an atom, right, as a tree is to the entire universe.
Damn.
So that's how small, even on atomic scales, we're talking about. And so, yeah, we can't probe there directly. We don't have accelerators to probe that kind of tiny distance. And we use our mathematics to push as far as we can. And that's a tall order. And so it is a tough problem.
That analogy you just gave me an entirely new perspective and respect for the entire field, because my answer to that, once you said that, is, oh, to hell with it then.
Take up something else.
Let's talk about something else. That's insane, man.
Yeah,
that's insane.
Yeah.
That's great.
But as we saw in the first question, it comes into play at the deep center of a black hole or the moment of the Big Bang. So these aren't questions that are irrelevant. They're just pretty extreme.
All right, Chuck, let's try to do some rapid rounds.
Who cares? These are so good. The questions are so good. The answers are so good.
Good. We got good people.
Yeah, these people are on point today, man. They're just on point. All right, let's go with Bruce Ryan. Bruce Ryan says, hiya, gents. Bruce Ryan here from Alexandria, Virginia. Everyone knows E equals MC squared, but how is it the formula actually used in practical terms? How is the formula actually used in practical terms? If you want to determine the energy of an object, what values do you plug into that equation? Is the mass in grams or pounds? Is the speed of light miles per second or kilometers per hour? Or does any of that even matter? Thanks.
Yeah, so where to use that formula? You don't use it much, of course, in everyday life. But if you're looking at a nuclear reactor and you want to know how much fuel needs to be put in, it gives you an order of magnitude sense, of what it will require. If you're trying to understand the sun and the amount of energy that's produced by fusion reactions, it gives you a sense of the scales that are involved. Now, how to actually use the formula? Well, the key thing that you learn in science is you have to use consistent units. So, kilogram meters per second is the units that we typically will use. And so if you want to use those for mass and for the speed of light, that's a really good way of getting an answer out in joules, which is a particular unit for measuring energy. But let me just say one more thing.
Well, just to be clear, the meters per second would be the speed of light, but then you square that. So it'd be kilogram meters squared, second squared.
Second squared
is the unit of a joule. Right.
Precisely.
Okay.
Now, I said that you typically don't use it in everyday life, but there's something misleading there. And I had a lot of arguments with chemists about 10 years ago about this point. They were all wrong. But
I bet I know what kind of argument we're having. They were thinking that the energy in their things had nothing to do with equals MC squared.
Exactly. For instance, an example that I use is if you take a flashlight, you turn it on, and you put it on an incredibly sensitive scale, the reading on the scale will go down over time because energy is going out with the beam of light, And that
Right.
energy has a mass equivalent, and that mass equivalent will register on an incredibly sensitive scale. And
Yeah, I've had the same debates
Yep.
with them.
Yeah.
Interesting,
They said
Brian.
it's only
But
nuclear. If it's not
yeah, no,
nuclear, it has no role.
Oh, well, that doesn't make any sense. We don't even have to go to the flashlight in an incredibly sensitive scale. Set something on fire. Okay, there you go. I mean, seriously.
No. Wait. All right, so a chemist rebuttal might be, Brian, that they have exothermic and endothermic reactions. Are you saying equals MC squared is coming and going in each of those reactions?
Equal MC squared is at work all the time. For instance, in the simplest example, take a pot of water and turn on the gas, right? As the pot of water gets hotter, if you were on a sensitive scale, it would register a bigger number, a small change, but a bigger number, because energy is going in. And if energy is going in, then the overall mass of this entity called the pot in the water is increasing. It's always at work.
So I did this calculation. So I drive an electric car. And so I wanted to ask myself, how much more does the car weigh on a full charge?
Good.
Right. And so I ran some numbers on that, some back of the envelope numbers, and it was so small. I was going to tweet it. Hey, look what I found. It was like, no, I'm not tweeting this. It was like 1,000th of an ounce or something.
Ridiculously small, but it's an important point, because so many students, obviously some in the field, conflate equals MC squared only with nuclear processes. And if it's not nuclear
that's what physicists, it's a physics thing. Yeah.
In fact, there's one chemist came back to me after a year of arguing and said, this has been a year of soul searching. I now realize that you're right. And I didn't really understand so much of what I thought I understood, which was sort of an honest response.
Yeah. And physics, there's no real understanding of chemistry without physics. And there's no real understanding of biology without chemistry. So Brian is justifiably cocky in that role.
Yeah. Yeah. Plus, we all know that chemists are dicks.
Of course.
Come on. Let's just be real here.
That's just common knowledge.
Common knowledge.
All right. Keep going. What else do you have?
Here we go.
That was not lightning round speed, by the way.
But guess what?
I keep slowing you down. I'm sorry.
It does make a difference. We keep getting in the areas that we otherwise would never get into on the show, which is fantastic. And we can just have Brian back again, people. Okay, it's a real simple thing.
He's got agendas in his own life.
I know he's got a life, but I'm selfish. So what can we do? Here we go. This is Serge. Serge says, hi, my question is regarding the subatomic world. If we could scale up an atom, what would it look like? Would it have some kind of shell? If yes, what would the shell consist of? The same question regarding the smallest particles. What is their composition and what is their appearance? If the quark is the smallest particle, what do you get if you divide it into smaller pieces? Oh, man, that's really cool. What does the subatomic world look like, man?
Yeah.
What does it look like?
This really challenges our intuition, because our brains and our eyes evolved for the purpose of survival. And to survive, we just need to be able to see on the scales of everyday life. And so the language that we
just to not get eaten by a lion.
Not eaten by a lion. So the language that we developed and the senses that we have are attuned to the kind of physics that dominates the scales of everyday life. And those physical principles are not the same ones that come to the fore. So when you're talking about an atom, we like to use language that resonates. We imagine we have an electron cloud. It's a probability cloud. Now, what does that mean in terms of visualization? Mathematically, I know what it means. There are a lot of locations where the electron might be found. But to actually see it, literally, I need to bounce some light off of it. When I bounce light off of it, quantum mechanics tells me I have affected the thing that I'm observing. So I'm not seeing the probability cloud any longer. I'm simply seeing the electron at whatever location the photon hit it. And so it's very hard.
Can I add something there, which is spooky? I mean, not spooky, it's disturbing when you think about it. Everything we see is larger than the wavelength of light that's reflected off of it. Right?
Yeah.
So if you have things that start becoming smaller and smaller than the wavelength of light we use to detect it with, the thing will just
disappear.
It'll just basically disappear. Yep. So Brian, you need light waves with wavelengths on the scale of the things in the atom you're looking at. Isn't that correct? If we're going to see it.
That's right. And so, and those are more energetic than we're used to, and they have more of an impact than the kinds of things, you've shone a light on a wall, the wall doesn't move, right? We don't feel the light bouncing off of us, but an electron feels the light bouncing off of it, and that interaction affects how it then subsequently looks. And so it's really hard to give an everyday visualization that's at all accurate for what things are like in a realm that we don't inhabit directly. I wish we could.
Wow.
I like it.
Okay.
I like it.
All right, here's a lightning round question. Travis Knopp says, hi, Doctors Tyson and Greene. Thank you for taking my question. I would like to know if there's a geometric center of the universe and what might we find there?
Me?
Is that you? You're there? You're there at the center of the universe?
Well, I have to say, one of my highest retweeted tweets ever was a simple sentence. I said, because the universe has no center, you can't be it. That's all. Somehow that deeply resonated with like everybody.
Yeah, that's good.
So Brian, can't we talk about a center of the universe if we include the time coordinate? And so we say, that's the direction of the center of the universe. Go there and you'll see it. And that direction is back in time to t = 0. Isn't that can I say that?
Well, you see, center to most people's minds is a special location within a larger reality. It's like you have all these other points that are somewhat secondary, and then you've got the center, which is primary.
Yeah.
And that we don't think applies anywhere or any when. So if you even go back to the Big Bang, the conventional story, although there are modifications of this, but the conventional story is all of space is in this point. It's not as though it's a point in a pre-existing realm.
Right.
And so even there,
so there's no construct. You don't have a construct.
Right. Yeah.
There's no construct within which you would find the center, even at the beginning. At the beginning, everything was at, quote, the center. Yeah.
Right.
But then we'd have to rethink how we use the word center.
Yeah, exactly.
And then even once that I want to say explosion, but
expands,
once the expansion takes place, it's like, what is the center of a ball? Where is the center on a ball?
On the surface of a ball.
On the surface of a ball.
Yeah, on the surface. That's the key thing. Because if you then imagine the center of it, then you're misled. But on the surface of a balloon, all points are equal, and there is no central point.
Right.
But if you do point to the center of the ball, that's where the whole ball was at the beginning, and then we're back to the original issue.
Precisely.
You can do that at any point on the ball.
Yeah, exactly.
At any point on the ball.
So the retort to your tweet might be, because the universe doesn't have a center, you and everyone else occupy the center. There's no location that's more special than the one that you occupy.
That's not as fun.
Yeah.
Yeah. That doesn't make people feel stupid. Makes them feel special. Nobody wants that. Okay. This is Andrew Coffey. Andrew says, hello to the best science communicators together, creating cosmic vibrations that will radiate knowledge, cultivate curiosity, and enhance our understanding. Please help me understand our limits. Will we ever reach a point where theoretical physics can no longer be explored, probed, or even proved experimentally? Maybe we are already there. Thanks, Andy C. from Vancouver, British Columbia. And he says, I truly love your work.
Excellent. So Brian, we all know a cocky physicist a century ago, but the turn of the previous century saying, physics is done. There's no more physics to be discovered, just a few decimal places and a few touch up some constants, and we should take on another field.
Yeah.
So where do you see the field right now?
Well, there's a huge amount of progress, but I can certainly envision that if we don't build new accelerators, and if we were to stop building powerful space telescopes, we wouldn't have any new data. And without new data, I can imagine, I don't know, 10, 20, 100 years of totally abstract theoretical research might grind to a halt. And it wouldn't be that we'd sort of reach the end. We'd simply reach the end in that era until we had the wherewithal to explore more fully. There has to be an interplay between observation, experiment, and theorizing. And so, yes, we're far from there now, but can I envision that if we lose the will to put the effort and the resources into understanding the micro world and the macro world with greater precision, could we reach an end for a while? Sure, absolutely.
Chuck, I just have to praise Brian in this moment because there are many theorists, he's a theorist, who hardly ever talk about, or think about experimentalists. They're in their own world. And who, Brian, who was it that said, never trust an observation unless it's supported by a good theory?
Yeah, I know the quote. I don't know who said it, unfortunately.
Yeah, somebody said that. Yeah. That's an asshole theorist talking. Right. But Brian is humble, and he knows that at the end of the day, good observations of the universe not only will constrain where he can or should think, but can also extend what new ideas might come out of that.
Awesome.
Let's flip in one more. We think we got time for that.
This is a good last one to dovetail on that last thought. David Lees says, "Hi, this is David residing in Chiang Mai, Thailand. What do you think will be the next major breakthrough or shifting of our understanding with respect to the universe?"
Yeah, I think everybody will have a different answer on this, but I think that in the next few decades, we're going to have a much more refined understanding of the Big Bang. The work that's being done in understanding quantum mechanics and gravity and black holes, I think ultimately the lens will be turned fully on cosmology. And I can envision that we will have a different, or at least more refined version of the theories that we currently have on the table. And in the best of all worlds, we'll finally be able to answer questions that we began with, like, what really do we mean by the singularity at the Big Bang? What really happened there? I think there's a chance that we'll have progress on questions like that.
Do you think there's any understanding we have that we feel good about that is at risk of being dismantled by new or better observations? So in other words, is there a shift in the paradigm, as they would say in the lingo?
Yeah, so two things. One, I mean, inflationary cosmology is the most refined version of cosmology. There are competitors now, and who knows, the scales may shift and our view on that may change. The other thing I would say is quantum mechanics. Many people are quite comfortable as fit. It's been around for 100 years and it works. But there are unresolved questions that many physicists don't really spend much time thinking about. And I can imagine that in the coming years, those problems, and they are real, I assure you they are real problems, may flare up, causing us to rethink the foundations of quantum theory.
I like that. Flare up.
Nice.
Up in your face. Well, Brian, it's been a delight to have you back on StarTalk. I don't want to assert my preferences on our audience because they express their own, but this is where my preferences and their preferences intersected and overlapped, getting you back on the program.
Thank you.
There's no end of cosmological queries that we have for you.
The truth is, every time we say that you're coming on and we put out a call to the listeners for queries, we get like 6 or 7 pages of them.
Yeah, they lose their shit.
Yeah.
Always happy to do it. All good questions. So.
All right, and your books are still out there. Elegant Universe. Give me the other
Fabric
two.
of the Cosmos, Hidden Reality, but the most recent is Until the End of Time, and my most favorite. So,
and is that out yet?
Yeah, that's
Till
out.
The end of time?
Yeah, definitely. Yeah.
Oh, cool. And who published that?
That was Knopf.
Knopf. Very nice. Until the End of Time. We'll look for them. All right, dude. Thanks. Chuck, always good to have you, man.
Always a pleasure.
All right, this has been Cosmic Queries with the one, the only, inimitable Brian Greene, friend and colleague, professor of physics and math, right up the street here in New York City at Columbia. This is Neil deGrasse Tyson, as always, bidding you to keep looking up.